Okay, so welcome to another video on resonance. We talked about resonance of amplitude. Now we're going to talk about resonance of power. So just to recap, we're doing a driven oscillator, and our notation is equation of motion is x double dot plus gamma x dot, that's a damping term, and then we have a omega naught square x. So this one was b over m, and this is k over m. This is the restoring force, and from the driving force we have a f naught over m cosine omega t. So the phase, this is the phase of the driving force. Well, the solution when time is much greater than 2 over gamma, so that you have a steady state. The solution I can write as x of t equal to some amplitude and goes with the same frequency of the driving, but it may differ from the phase of here by a phase lag, phase constant called phase lag in this context. We also can write this as, you can see, there will be cosine omega t, and this is sine omega t. So there we can also write it is called elastic amplitude cosine omega t, and then absorptive amplitude sine omega t. That has to do with this one has the same, this part is in sync with that, and this is 90 degrees out of sync with that. Okay, so also, all right, we figured out what the A looks like and delta looks like. So let me say A has to be f0 over m is square root of omega naught square minus omega square plus gamma omega square, and tangent delta was like a ratio of these two guys, gamma omega over omega naught square minus omega square. And one way to think about this was think of this side and right angle triangle, this side gamma omega and this side omega naught square minus omega square, and so this angle will be delta. So you can, from here you can get sine delta and cosine delta. You can, going back there, you can see if we expand this, this will be related to A cosine delta, so that's will be that, and this will be, from here it will be A sine delta. So you can get these amplitudes by just using this triangle and get the cosine and sine delta, and you have an A. Okay, so what's the power? Power of a force will be power of a force. You can, it's called instantaneous power. We define as instantaneous power. Instantaneous power. So you have a force F. I want to know what this instantaneous power is. So this force is acting on something, and that something's displacement is, say, r, and that displacement changing in time, and then we define velocity from there. Instant power is a force acting on a system that has velocity v at that instant. So you can say this power will be a function of time, will be f dot v, or you can say you have f dot dr dt, and you can see the numerator will be some work done by this force at in a very small interval of time. So this is the rate of work done by force F at this instant. Okay, here the system is all along the x-axis, so for us it's simply fx vx. For us, you have x given, so this will become, this fx is simply the driving force. So for us, driving force is f0 cosine omega t. So that's this part, and vx part is just take a x derivative of that, dx dt. Well, when it's, we could use calculus in this or this, but it turns out using this is easier to do calculation, because just in a moment you'll see sines and cosines are separated. So if I do this out, I have f cosine omega t with elastic. I get a, let's keep in a simple notation, a elastic cosine omega t, and then I have absorptive sine omega t, right? So this so far so good. So this is the give me the instantaneous power of the driving force, and to look at it, it actually has a elastic f0 and cosine square omega t, and then this is not correct, because this should go into minus omega and plus omega, and this will become sine omega t, and this will become cosine omega t. So I've got f0, so f0 omega elastic minus sine cosine omega t and sine omega t, and then this will be plus f0 omega a absorptive cosine square omega t. You can see that this will, you can write this as a half cosine 2 omega t, and you can write this as in a double angle, sorry, this is some making mistakes here, sine 2 omega t, and this one will be 1 plus cosine 2 omega t over 2 for that. So this instantaneous, if you plot the instantaneous versus time, plot the instantaneous power versus time, you see that you f omega absorptive over 2, so it's going to be that value, and then this will fluctuate with time, and that part will fluctuate in time. So it's going to be, it's going to go up and down, it's going to be up and down, up and down, up and down like that. Okay, so the power is actually fluctuating, and we would like to know what's the average power, not highly fluctuating quantity. Maybe in some places you would like to know what's happening, power at this instant, power at that instant. But more applications are about average power. For instance, when we use say this was some kind of electronic transition, and this was electromagnetic wave, then the frequency will be very large, very high frequency, and our instruments will respond to average power. Okay, so so far so good. So this is the instantaneous power, and we would like to make an average of this. From here you can see that average, if I take a time average, and something has a period, so if I have average over one period, it's going to be 0, right? So this thing will not contribute in the average, and this part will not contribute in the average. Only this part will contribute in here. So you can almost guess at what the average will look like, right? So the average power, which we can write like this, or so these are like time averaged power. Basically what I'm doing is I'm doing an integration over one period, and just go from 0 to period p of t, and what's the period? You can go back to the period of omega t if you like, or period of this function itself. Period of this function frequency is 2 omega, so the period you can do is will be 2 pi over 2 omega. So because that's the frequency. So it's you can just do over pi over omega, and you will see that this goes to 0 and that part goes to 0. So what do I get? P average. I get F0 omega AB, F0 omega absorptive, that the one that was with the sign, divided by 2. Let's see what the absorptive looks like. This one was sine delta, so this is F0 omega over 2, A sine delta. So if I look at A and create sine delta from there, so this will be F0 omega over 2, F0 over m, and sine delta will bring one more factor of this, and gamma omega at the numerator, gamma omega over this whole thing. The square will go away, omega naught square minus omega square plus gamma omega square. Okay, so we want to see what a plot of this looks like. It will show a resonance-like curve, as it will have a peak. There will be a frequency at which it will peak. It's not going to be the same frequency we found before. Okay, so you can put all the omegas in one place. So this omega you can say omega square. Can also erase that out of the way so it's clear what we are doing. Okay, so there's a gamma square here. We can put a gamma square here and put a gamma here. So this part has the omegas in it, and this part are the independent omega. So we can say the average power is actually, we can treat as a function of the driving frequency and study that. All right. So what it look like when it's omega? If I plot this versus omega, I see that when omega is 0, this is 0, this is 0, but it leaves a non-zero here, so it's a 0 over finite. So that is 1 point. When omega is infinite, there's nothing competing here, so this guy wins. Over here is 1 over omega to the power 4 wins. So this goes as dies very quickly, goes as 1 over omega squared. And somewhere here is a peak. Okay, so where is the peak and what's the maximum value of the peak? You can treat this as a function of omega and take a derivative, and you can show that the peak actually is, very interestingly, omega 0, which it's related with the system property K and M. So this is the frequency at which the oscillator will oscillate naturally. So this is also called natural frequency. So if you were going to do an experiment, so if my oscillator and the damping is always a black box, suppose a black box, and I didn't know what mass was, what spring constant was, but if I hit it with a driving force and I vary its frequency, and wherever and I find what kind of power getting absorbed by the system, I will see that there's a frequency at which its maximum power is getting absorbed by the system, and that frequency that I can find by doing the experiment of this guy, right? I'm controlling what frequency I'm putting, so I'll come to a frequency at which I get most power, and that frequency is actually same as this black box system inside its natural frequency. So systems which are, this is one way to figure out natural frequency of the, if there's a single frequency out there, there will be a single peak. Now we'll see in the coupled system, when you have say 2 blocks and you're driving it, and there are 2 natural frequencies there, right, 2 normal modes, there will be 2 frequencies at which this thing will happen. So this is tells us an experimental way of finding out by interacting with the system, by controlling what frequency I'm driving at and what's happening to the energy. This is power is energy, and we can actually tell what are the system's properties. And this is a fundamental way we probe many systems. Okay, so let's see what else can we do here. So what's the maximum power? Well, if this omega as the peak, I put it here, that kills this guy. This goes to 0. This becomes, so this factor becomes 1 at the maximum. So 1 at max. So this is the average power at the max. So this is F0 square over 2m gamma. That's kind of the maximum. What's another property? Well, it turns out some systems will give you a very sharp peak, and some system will give you a wider peak. And that has to do, we can look at half the peak. You can take a power, and this is half the F max, F0 square over 2m gamma. So this is half the power max. So there are 2 frequencies at which this happens, and this is called width at half max. You can find this very easily by setting P average equals, it is P max, and this thing over here equal to half of P max, right? So when we set this equal to, this is the any P, so that's the P, this, so when does this equal to that? And when you solve this for omega, you'll find this thing is a quadratic equation, and there are two values, and from there you can tell what's the delta. And I'm going to leave that as an exercise. So this thing is called delta omega at half width, and that is actually equal to gamma. So if you did experiment and you did drive the system at different frequencies and measure the power absorbed, and you got this resonance, pressure resonance curve, this is called resonance curve. You got this power resonance curve. Then from the width, you can also get how good an oscillator it is, because you can get a gamma from it, and you get an omega naught from it, and gamma and omega naught together give you the Q factor of the oscillator. So we didn't know beforehand what the system is, a black box. You can say the Q of this oscillator will, if this is a good oscillator, then it's omega naught over gamma, you might remember. So from the width I get the gamma, and from the peak I get the omega 0, and I can tell how good, I can characterize what's the Q of the oscillator. If the Q is very high, it means very good oscillator. So I'm going to stop now, and I'll post this video for you to study. Okay, bye.